This lecture is about time dependent perturbation theory, and the plan of this lecture is that first I will develop the derive the basic I will start with by the basic notions of time dependent Hamiltonian, which we have already learned a bit through the Schrodinger picture and interaction picture and all that, but here I will use those ideas and work out a simple two level system which is exactly solvable first, and see how to handle and what kind of physics you expect from time dependent Hamiltonian. And then I will go to a generic formulation for the problem which cannot be solved exactly. So, you use perturbation theory. I will work out the basic formulas of perturbation theory, like what kind of questions you ask, or what kind of question you are often interested in this kind of system. We will discuss that, and we will discuss how to answer that question. So, after that I will derive the same or show how to work out the same same formula and same kind of answer, same questions using the interaction picture formalism or Dyson series and all that which we developed in last class. So, you will see that it will be a much more elegant and compact derivation, and it has much more scope of doing further things. So, that will be basically the formalism, and then I will do some applications. So, there are generally several typical type of examples you encounter often in physics, and these are the kind of examples also which are kind of well understood. So, I will discuss a little bit of so I will mainly discuss those problems which are well understood and usually found in textbook, such as a constant time dependent perturbation, which is basically you switch on a Hamiltonian at a certain time or switch it off at a certain time. Then I will discuss harmonic perturbation or something which sinusoidally varies with time, and some special cases which is like a sudden approximation and adiabatic approximation, which is basically a perturbation which is suddenly switched on and suddenly switched off, and then another class where the perturbation is slowly switched on and slowly switched off, something like that. So, we will do all these kind of examples which are basically very common in physics and experimental situations, and quantum mechanics is incredibly accurate in predicting and calculating what kind of physics happens under such scenarios. So, we will discuss those examples. We will see it will lead to some very interesting concepts, some very advanced concepts like Berry phase and all that in the adiabatic approximation section. And I will discuss briefly two interesting research grade problems. One is if time permits, one is a thing called Floquet Hamiltonian, in which you periodically kick the system with a sharp perturbation, and it's a kind of non-equilibrium physics problem, and we will see what happens because of that. And another non-equilibrium problem in which you take the system through a quench and evolution cycle, and what kind of non-equilibrium phenomena you expect from that. So, that is the overall whole plan of this lecture. So, let me start with the formalism. Before that, let me set up the stage for a simple time dependent Hamiltonian. So, let us say we want to work out how does the states of a system evolve in time for a Hamiltonian which is of the form h t is equal to h naught plus v t, where h naught is a time independent part and we know how to solve it, and v t is a part which is like the perturbation which we do not know how to solve it. That is a typical setting of a perturbation theory, and except the difference is here the v t is time dependent, and as a result the h t is time dependent. So, let us recap what happens in time independent in the time independent problem. You have a psi naught which you can express in the eigenstate basis, expand in the eigenstate basis as C naught 0 n, where C naught 0 is the projection of psi 0 or the time independent wave function on the states in eigenstates n, and this is the Schrodinger equation it satisfies. And if you want to know the time evolution of this system for a time independent Hamiltonian, you just solve. So, this is h naught, I meant to say this is h naught. So, you do this just write down this time evolution equation and so expanding the psi naught in the eigenbasis, you can write down it as e to the power minus int cn0 n. We often refer it as the CNT. So, as if the coefficients are evolving with time, and these are stationary states, they are evolving in time with the simple phase factor. So, that is how we deal with the dynamics of a time independent problem. So, now let us look at the situation what happens when I add a Vt which is time dependent. So, it is like a system is subject to an external influence which is changing with time. So, not necessarily you can write it in H naught plus Vt form, it could be just some Ht itself, not a additive like H naught and Vt. So, as an example you can think that let us say spin in an external time dependent electromagnetic. So, we have looked at the problem of spin in external time dependent magnetic field. Now, time independent magnetic field, but now we are considering time dependent. So, I should have written dependent here, not independent. So, that is an example of this kind of scenario. So, expand again the initial state at time 0 which is H0, there is no Vt yet. So, expand the psi 0 in these eigenstates, and then you apply again the whole Hamiltonian, but now this is Ht, where Ht is H0 plus Vt. So, in this form. So, the H naught will give you this factor, and the Vt will give you some complicated factor which you do not know, and you write it as some CNT. So, this is the time dependence which entirely comes from Vt. Now, we expect that the Vt has some small factor just like perturbation theory, and we will argue what do I mean by when that can be decided as a small enough. That kind of discussion will of course appear, but since we are applying the machinery of perturbation theory, you can expect that it is a kind of perturbation which does not cause a level crossing. So, now we will using this kind of in such a scenario using the machinery of perturbation theory, we will like to compute the CNT, because that is what we need to know in order to know the dynamics of the state psi t. That is the only unknown in this equation. Okay. So, we will do this thing in two different methods. One is a direct method which is similar to the time independent perturbation theory, and you will find it in any most textbooks, like Griffith does a fine discussion on this. So, the reference for this chapter is a combination of many books actually. I used many books for this chapter like Sakurai, Shankar, Griffith, Landau and Cohen-Tannoji, but you may not want to read all these books. So, I will suggest you to just read Griffiths and Sakurai. You will get the whole point if you just read these two books. For certain things I have used some other books and some independent notations. Okay. So, now we will do first using the simple methods as like the time independent perturbation theory, and then we will do the same thing using an elegant and compact method which is the interaction picture. So, let us look at the formalism, start looking at this formalism using a simple picture. So, take this equation 4 which is the equation we actually want to know the CNT, and plug it into the Schrodinger equation. So, this is the Schrodinger equation, H psi t is I h bar d dt psi t, or H is the full Hamiltonian, full time dependent Hamiltonian, and psi t is the full wave function which you are interested in. So, if I plug this in this side, it will be just become this, and this side that this derivative will give me these two terms. So, now you use that n0 satisfies the, because n0 is an eigenstate of H0, the independent part. So, using that we can simplify this to be of this form, that I h bar sum over n e to the power I e naught h bar d dt c n t n naught is equal to sum of n c n t to the minus I n naught h bar v n naught, which is a very simple simplification, where I just swapped the right hand side left hand side from the previous page. Now, we use the orthogonality of the H naught eigenstate, because these are orthonormal eigenbasis the eigenstates form orthonormal eigenbasis, and we using that we can project out the time derivative of a particular coefficient CFT. So, you want a one particular coefficient CFT, because this is a summation form coupled equation. So, you want just one. So, you use this, so put this f naught bra on both sides, and using this orthogonality you obtain this differential equation, which is d dt CFT minus I by h bar sum over Cnt to the power minus I f naught minus E n naught t h bar f naught b t naught. Okay. So, now doing this using this simple Schrodinger equation for the time independent states or the unperturbed part, now we can work out this this equation. So, just to simplify this form, you will see whenever you have this h naught n naught, we will put this in E n naught n naught and so on. So, that will lead to these simplifications. So, now and here, as I said, I swapped these two sides. So, this is how this equation looks like, and then we will use the orthogonality of the h naught eigenstate to project out the CFT, which we just discussed, and we will obtain this equation when I apply the f naught in both sides. So, this equation, now I have written it in a matrix form. So, you can see what does this equation mean in much more clear manner. So, this is d dt CFT, some CFT, which is the unknown equation. So, what this equation is actually? This equation is it gives a dynamics of this coefficient CNT, which we actually want to know in terms of the known factors, which is this f naught, p naught, n naught, E f naught, E n naught, and so on. So, now it is a coupled first order differential equation which we want to solve in order to know the CFT, which is actually our unknown quantity we want to solve. So, this equation can be written in a simple matrix forms. So, it becomes I h bar, this side becomes this, if I just take the I h in this side, C 1 dagger, C 2 dagger, C 3 dagger, so on. This is a matrix whose elements are where this quantity does not appear in diagonal, because in diagonal f and n are same. So, this will disappear in the diagonal, only in off diagonal it will appear. So, I will use the compressed notation W omega n m, which is nothing but E n minus E m by h bar, and that is this factor. So, I have so now notice that because it is a bit cumbersome to always keep these not factors like E n naught, n naught, f naught. So, I will drop this not factor from the superscript from now on. Mostly I will not use it, sometimes in some cases it might reappear, but most of the time I will not use it, and you just keep it in mind that there is this not factor. So, we basically it is very simple, similar to first order perturbation theory, because in first order perturbation theory we know the object we calculate often is this matrix element, the perturbation term with respect to these two, here the V is Vt, also remember that, but in in time dependent problems this is just V, and we compute this between these two states of the unperturbed part, and here this factor appears which is also dependent on unperturbed form, and this is gives the dynamics. So, we want to solve this equation, and for brevity I am dropping the not subscript, not superscript or subscript, whatever, from this from now on. So, this is actually not an easy problem to solve. It is a coupled n differential equations, and in most of the time you cannot actually solve it exactly, and that is where you need perturbation theory for most problem. But remarkably there are some simple systems like two state systems. I mean, it is not remarkable that you can solve it for two state systems, simple, because this is just a 2 by 2 equation for two state system, which you can, a coupled pair of differential equation which you can solve. But what is remarkable, there is immense practical importance for these simple systems. A lot of application and experimental thing and technology is dependent on these two state system, time dependent systems. So, let us look at the example of that. So, here I write down that coupled differential differential equation again in the compressed form by dropping all the not superscripts. So, let us look at this. As I said, there is this two state systems we will now solve, where the B f n t, this is already itself a time dependent part which I do not write here explicitly. So, let us and this equation is true always, like even if it is time dependent or time dependent does not matter, this evolution equation is always true, because we have not made any approximations in deriving it. So, let us consider a two state system with a harmonic potential that connects these two states. I will come in a moment what do I mean, and this is a rare example of a problem which is exactly solvable and of great practical importance. So, the H naught for this two state system is diagonal. So, if I write in this notation, it is basically E1 and E2 are the two diagonal entries of this 2 by 2 matrix, and the perturbation is something which connects these two states, and that is given by a harmonic time dependent perturbation, which is given by V naught e to the power minus I omega t coupling these two, and then its Hermitian conjugate V naught side to the I omega t. So, if I write in matrix form, this Hamiltonian in this basis looks like E1 E2 in diagonal, and this potential time dependent potential in off diagonal terms. So, we want to solve this using this coupled differential equation. We want to know the full time evolution of the full wave function of this two state system. So, what is this time dependent potential doing? Just think a moment physically. It connects the two energy eigenstates of H naught. So, H naught energy eigenstates, this is a diagonal Hamiltonian. So, the H naught itself is already in the eigenbasis. So, 1 and 2 are eigenstates of H naught. So, this V naught, this V potential basically connects these two eigenstates, and that allows, so you can expect naively just by thinking physically what will it might happen, because normally if a system is in its eigenstate, it does not it stays in that state. So, that is, you know, these are like called stationary states, and if you start in an eigenstate of a system, you stay there. But these eigenstates of H naught are not eigenstate of the full problem H. So, when you apply H, the system is supposed to go back and forth between the states 1 and 2, and that is we call it a transition. So, this perturbation basically allows a transition between these two states 1 and 2, and we will explore that what is the character of this or nature of this transition. So, this is an exactly solvable problem, as I said. So, at time t equal to 0, let me assume a simple thing that let us say the lower of these states. So, this is E1 and E2, they are the energies. So, let us say E1 is smaller less than E2. So, I call this as the ground state. So, let us say at time equal to t, the system resides, or the particle, if it describes a particle, is resides the lower level, at the lower level of this. So, C1t is 1, C1 at t equal to 0, and C2t is 0. So, the equation of motion will couple these two states. So, for dC1 it will be given by this equation, where V12 is basically e to the power is 1 V2, like this between 2, and this V has a time dependence e to the power I omega t. So, that gives the e to the power I omega t, and there is a e to the power minus e to the power I omega 1 to t, which is coming from this formula. So, that is basically the equation of motion of for the the dynamics of the C1t, the probability amplitude of being in the first eigenstate of H naught. And similarly, I can work out the equation for C2 dC2 dt. It will be just this. So, we know it is just a pair of coupled differential equation. We know how to solve it. We take a derivative here again. I will get d2c2 dt2, and I will have dc1 dt1, which I replace it here, and now I will have equation of motion purely in terms of C2. So, when I do that, I get this simple harmonic, this simple second order differential equation, which we know very well how to solve. And now, let us try to solve this differential equation, and we know that the condition for to solve a differential equation, we need this initial condition, which we know for C2 is it is 0, time t equal to 0, it is 0. So, let us use the trial solution, which is e to the power I omega t. This omega is capital omega, and that will give me the following characteristic equation, which is just a quadratic equation, which will have two roots like this, and if I plug into C2t, I will obtain this solution. So, now I use the initial condition, which is C2t is t equal to, because there are This is a second order equation, there are two unknowns. So, A and B are the two coefficients. So, if I use this this initial condition, I will obtain that the B must be equal to minus A. So, the C2T will be this. So, A is basically the only unknown now. So, this is my equation of C2T, and now we will like to find the A, and we know we need two initial conditions, just one is not enough. So, we will use the initial condition for once we use C2 0, C2 at t equal to 0, now we will use C2 dC2 dt at t equal to 0. So, we will plug in this equation of motion for dC2 dt at t equal to 0, and we know that the C1 is 1. So, from there we will get the condition on that, and C1 at t equal to 0 is 1, and that when we plug that in we get the full solution of our C2T. It's a little cumbersome, but it's quite simple when you take, because we are interested about the probability eventually. So, the probability of finding the system at the upper level 2 or upper state 2, which is normally not possible in the absence of the perturbation, but the perturbation now allows the transition to the state 2, is basically P2 C2 square, this equation. And it is, you can see it's a harmonic equation, it is a sinusoidal periodically in time, and if we know the P2, we obviously know the P1, because there are only two states. So, P1 plus P2 must be equal to 1. So, we also know the P1. So, now notice what happens to this amplitude of this probability. So, this probability varies with time, like in a sine function with some amplitude, and that amplitude is the maximum when omega is equal to omega 2 1. So, that is basically we call it the resonance condition, and because the amplitude of oscillation is large, so that is what we call as resonant condition. And what does it tell us about the system by this solution, that what the system is doing? So, the system basically at time t equal to 0, it will absorb energy from the time dependent field, and after a time period which is given by this period, it will be found in the excited states, and then it will be found in the ground state again and again excited state, and that way it will oscillate. And since it is, when it is going from ground state to excited state, it is absorbing energy, and when it is going from excited state to ground state, it is releasing energy. So, it is a cycle of energy absorption and emission, which is sourced by the time dependent perturbation. So, if I plot it, it looks like this. So, the C1t, it starts at C1t and C2t is 0 at time t equal to 0. Then the C1t, if I plot this solution here, the C1t falls, it goes to 0 and the C2t rise. So, at this point the particle has a probability 1 to go in that excited state, and that means it is absorbing energy. In the next cycle it goes down and the C1t goes up. So, that means it goes again to the ground state. So, it goes in, oscillate between these two states and goes in a circle of absorption and emission of energy infinitely. So, that is basically the physics of this system. And so, the Vt, so as I said that 1 to 2 is absorption, 2 to 1 is emission. So, this 1 did not come out, but this will be just 1 kT. This is a source sink kind of situation. Now, this absorption emission circle does not need. So, this is something, this plot is made for omega equal to omega 2 1, which is the resonating condition, which is where this is 0 and the time period is given by this, and this is also 0. So, this is the maximum amplitude, but it will still have the sinusoidal form even if it is not at the resonance, only the magnitude of the oscillation will be reduced, and the C2T square is like, it will not be fully into 1, it will be a finite probability of being in 1 and 2. So, this thing won't be 0 and this thing won't be 1 either. So, it will be a less amplitude or less drastic thing, but it will be still some similar cycle. And so, if I plot the C2T square amplitude with respect to omega, so at omega equal to, this is the resonant condition, that is where it is maximum. So, that is basically the maximum amplitude or resonance condition, and as I go away from omega, it reduces like this Lorentzian form. and we know that this width is called the full width at half maximum. So, this thing is weaker as so now you can see that and this object is equal to 4 b by h bar, and this is the resonance peak, and we can see that from these expressions that weaker the time dependent potential, the narrower the peak gets sharper and sharper. So, it gets like you have that is a characteristic property of this kind of thing, and this is like you have to find exactly in that case once you tune the frequency of the perturbation very precisely to the resonance condition, you get a very sharp peak, indefinite oscillation, and that is actually a fundamental working principle behind lasers. So, for ammonia measure, ammonia is a two-state system which you know, which you have learned from Feynman lectures. So, for ammonia, this idea is used to make something called maser. Maser is basically laser for microwave radiation. Laser is basically light which you can see, microwave you cannot see. So, they are called maser. So, that has these two states S and A, which are usually called, with energy difference 10 to the minus 5 electron volt, and this in this case this idea is used to produce a spontaneous emission of light and coherent light, which is amplified, and one that is behind the technology of maser. And also we will see laser is also based on similar idea for a little more complicated system and slightly different system, but the idea is same. And that is one practical application, and there is actually many practical application. Another is called spin magnetic resonance, which tells you how a spin half behaves in an AC magnetic field, and that is the working principle behind technologies such as NMR and atomic molecular beam, and which allows us to measure magnetic moment of spin systems, and many important experimental thing we can do is because of this idea. So, that is basically all I wanted to tell you about this exactly solvable problem. And now we will go to the formalism of certain problems which cannot be exactly solved. So, let us look at the equation 5 again. This is the equation 5, or this form of equation 5, a more compact form of equation, the same equation. So, this is not necessarily, this is something you can solve exactly. First of all, if there are n states involved, the Vfn is something complicated, and so on. So, then you cannot essentially solve this equation exactly, and then you have to use the ideas of perturbation theory. So, now let us look at one such, let us look at the formalism of that kind of problem, how to solve using perturbation theory. So, as I mentioned, there is a complicated set of coupled differential equation that is difficult to solve, because this dCf dt is coupled to every other CNT for n by n state system or infinite state system, for which the matrix element is non-zero, or in other words, due to the time dependent potential, there is a finite probability of transition between the eigenstates of the unperturbed problem. So, this is a very complicated object if you think about it. Complicated in the sense there is no way to a priori predict it unless you calculate it. So, we will use actually a perturbative approach to solve this complicated problem, and like before, we will introduce a small parameter in front of the epsilon, which is varies between 0 to 1. At the end of the calculation, we will place this epsilon to be 1, but that is a small parameter we require, just like the idea before. So, this is my unknown quantity, and I will expand that in power series. That is what we do in perturbation theory, and put this into the equation 5 which we want to solve. So, what happens when I put it into equation 5? I get this form, and we know, just like in perturbation theory, this equation to be satisfied all the time, each coefficients of this power series, this is a power series equation, each coefficient of this power series have to be 0. If I take everything in one side, it can be written as a power series which has a coefficient, and that has to vanish. So, what is the equation which it satisfies from that condition at order epsilon to the power 0? We get only this term, because in epsilon order you have this, and because of this epsilon all these terms are with epsilon. So, nothing is there at epsilon order from the right hand side, and left hand side is only this. So, this just tells CF0 is 0 as 0th order. This 0 means the 0th order. So, at time t equal to 0, now we will use the initial condition that time t equal to 0 the system is an eigenstate I naught of H naught, which is a very special condition, and you will see in lot of practical problems this condition is not true. And but we will see how to handle that, because even if that condition is not true, you can write the whatever state it is, you can expand it in the eigenbasis, in the complete eigenbasis of H naught. So, then you can use that fact to work out everything, and if you know how to do it for an eigenstate I naught of H naught. So, let us start with that simplistic condition, and if that is true, this tells you that the CF0 does not change with time. So, that means the CN0, when I solve this, it must be, so I should have written actually CF0, but I wrote CN0 by mistake. So, but either way, see, then you can think this as ddt Cn0 instead of calling it Cs. So, f by f I mean to say final. So, basically the CF0 will become delta Fi. So, that is what I mean to do here. So, it will say the system will stay in that same eigenstate. So, that is certainly not true. We know that is certainly not true in a time in this problem, but the 0th order answer is that. So, CF0 is, so now here I write it correctly. So, the CF0 is delta Fi and all other things are 0. So, whatever the system started with, it remains there, even though it is not a no longer an eigenstate. So, the stationary state remains. But this is the 0th order answer. Now, we will improve on that. So, look at the correction. Let us see what is the correction on that. So, what is the first order answer? The first order answer satisfies this equation. So, the CF1 is now the unknown quantity. This is the sum over Cn0 and this, and that is the known quantity, this, and we know that all of these things are 0. So, all of these things are 0. So, actually this should be, I should have written this as 0 and this as k. This should be 0 because they are just saying 0th order, all other C's are 0 except f, that is the state we target, and that f is basically equal to I. So, now in the first order, this side is unknown, this side will be the sum over all these states, and only the f is 0, f is non-zero, everything else is 0. So, it will satisfy, it will become this. So, now I can integrate this equation and I obtain CF1t as equal to minus I by h bar dt prime e to the power minus EF0 minus EY0 t prime by h bar f0 vt prime I0. So, that is my first order solution. So, now what is the solution together up to first order? Now, the CFT is basically delta Fi minus I by h bar, this form which we just derived, plus other terms. So, let us step back a bit and see what does it tell us. So, this tells us the transition probability of the system if the system is initially in an eigenstate I naught. So, that is the thing we are interested in, and that is what we saw in the exactly solvable problem also, that we are interested in that how the system transit between the eigenstates of the unperturbed problem. So, if the system is an initially at eigenstate I naught of H naught, this equation tells us what is the probability amplitude of it being into an eigenstate F naught after time t. So, that is what this equation tells us, and now we will and because of introducing the time dependent perturbation, and we know that that system would have remained in the same state if there would not have been a time dependent perturbation. So, this formula is pretty generic, by the way. This does not need to be a time dependent term, it is any perturbative term. Even we will see that we will do also constant perturbation, we will see how it is general. So, now let us look at try to derive the same equation 12 using interaction picture. So, it is a bit of tedious and hard work to derive all the higher order terms, like we derived the first order term, then second order, third order onwards, it gets very complicated and difficult by the method we just did it. So, now we will see a simple method which is based on the formalism of interaction picture, how to derive the same formula, and that will allow us to calculate the very higher order term in a very simple manner, and it will even allow us to represent this whole thing in pictorially and such that we can remember the whole picture very simply. So, that is the advantage of this notation and this formalism, which we will just which we will learn based on the interaction picture we learned before. So, what does the interaction picture says? The interaction picture says that the psi interaction and time dependent is basically equal to where the dynamics is related to the Schrodinger eigenkette by this relation, where e to the minus t is the h naught, its dynamics is by the independent part of the, when I write down the h as h naught plus v, dynamics given by the h naught part. So, the psi st is the Schrodinger picture time dependence, which I can simply expand and write it in this way, and we know it is just C and T. So, you can look at the dictionary I wrote down in the previous, at the end of the previous lecture, that how to go from one picture to another picture, and using the dictionary we know this is the form, and now we can use this to write down. So, the psi I t as C n t in naught, where C n t contains all this like these two terms will cancel when I let it go in, and then I will just be left over with the C n t, and the C n t is nothing but the projection of psi I, the interaction picture wave function on f naught. So, that is the psi I t as we written it in terms of the n naughts. So, now remember that the interaction picture, the time evolution operator or the propagator, it satisfies the following equation, which again you can read it off from the dictionary. It is I h bar d dt psi I t v I t psi I t, and a formal solution for that can be written by writing this at u, which we again discussed this already in the previous lecture, that u I t is 1 minus I by h bar 0 to 2 d t prime v t prime u I t prime. Now, this is an equation where both sides has u t. So, we can obtain this solution as a power series form, again something we discussed before, it is called the Dyson series. So, this u I t is equal to 1 minus I by h bar d t prime to v t t prime, where t prime is less than t, less than or equal to t, and this u I t prime can be rewritten again as a similar formula, which is from 0 to t prime, and here inside the integral there is t double prime, where t double prime is less than equal to t prime. So, and so on, you can carry on this process. So, the u I t is now a power series form in I by h bar, which we discussed in previous lecture, and this is that power series form. So, revising this thing, so let us move on how to use this to calculate things we want. So, equation 14 is a full series sum, as we discussed before. It is not a perturbative thing, it is a full series, it is a power series in full form, because it is not a small parameter object, because h bar and all are in denominator. But let us now introduce our small parameter, which is v I t as a coefficient of v I t, epsilon v I t. So, now here it is increasing in that power. So, if there is epsilon here, there is epsilon here and here. So, if epsilon square and epsilon cube and so on. So, now it becomes a power series in epsilon. So, automatically when you introduce this small parameter, this u I t becomes a power series, a perturbative power series, and we will hope that the series will converge sufficiently rapidly, such that if I just calculate the first few terms, it will give a good approximation of the time development of the, or time evolution of the system, and we will see that how this works for some practical problems, but in principle it makes sense what we have done so far. So, now returning to the problem, let us say my psi I 0 is I 0, by where I assume this the system is entirely is a particular eigenstate I naught, and we are interested to compute the transition amplitude from I naught to f naught. That is what we have discussed already, that is the quantity of interest we want to calculate. So, using this equation 14, this thing can be written as using this power series in this form. Sorry, this could be written in this form. So, this is the first term, which is f naught I naught, just the delta f I. This is the second term, which is I by h bar, where f naught is this V I t is the interaction picture potential, which we write in the Schrodinger picture. When I do that, I again look at the dictionary in the last lecture. So, that will give me this form, and we can evaluate this very simply, because these are the eigenstates. This will give me E f naught and this will give me E I naught. So, this will become the form, and that is exactly the equation 12 which we already derived. So, it is a very elegant and simple formalism, and very quickly we can derive, very simply we can derive the transition amplitude which we actually wanted. So, the probability of finding, what will be the probability of finding a transition from I naught to f naught? It will become, in the Schrodinger picture, it will become CFT to the minus E f naught t by h bar square. So, which is nothing but the CFT square, because this is just there is an I factor here. So, that is just this square of this amplitude. So, as I promised that the whole point of doing all this using this notation is that things become much simpler. So, now we will use this interaction picture Dyson series form to do higher order perturbation theory. So, this is the formula for all the higher order terms. This is the term which we just worked out, and there will be all these higher order terms. So, let us try to see that how can we calculate this. So, for that let me recap again the psi I t psi s t relation. So, here psi s t at time t. So, now I can write down the time evolution equation, which gives me the transition from t naught to t. So, now I can write psi s t as t naught, which is a completely static object, because now the time dependence is taken out here like that, and this becomes so now I rewrite this as the, so now this is the time dependent interaction picture eigenstate, is a time independent interaction picture eigenset if I write transit everything to the interaction picture. So, this is how the time dependence looks like. So, without deriving it, again you can approach the dictionary, you can see how the eigenstate evolves. We know that the eigenstate evolves by the h naught in the, or the wave function or the state ket evolves by the h naught in the interaction picture. So, this is the formula we get, and we rewrite this as, so if I write this thing as U I, because this is nothing but the Schrodinger time evolution, which is sandwiched between this time evolution and the interaction picture, we obtain psi I t, how psi I t is related to psi I t 0 and that is by interaction picture time evolution equation. There is nothing special about this equation, you can read it off from the dictionary even if you do not want to write it down like that. And this is what we get again from the dictionary, is that U I t t 0 is related to U s t t 0 by this formula. So, now we want to do everything in Schrodinger picture, that is the picture which is familiar to us and makes maximum physical sense. So, let us just look at the relation between the transition probability, because so far we have worked out things in the interaction picture, but let us just look at the relation between the interaction picture and Schrodinger picture for a generic f and I, not necessarily f 0 and I 0, but we can think it also and f 0 I 0. So, if I use this formula, all this formula, I will get this form. So, when I take square, which is actually what I want to do for probability, there is no difference between these two by calculating the square between U I or U s, and that is why here also we can compute this interaction, even though we are calculating everything in interaction picture, it is nothing but the Schrodinger picture square, which is what we obtained already using the simple Schrodinger picture formalism. So, that is how we derive this. So, now let us try to understand that how to do it for higher order terms and what are the physical interpretation of that. So, let us say before that let us discuss one more small point. So, if we take the matrix elements of Ui between initial and final state that are not energy eigenstate, let us say some A prime and B prime which are not commuting with Hamiltonian, which are eigenstates of some operator A and B, but not commuting with Hamiltonian. So, they are not energy eigenstates. So, then this relation is no longer true, because earlier this was F and I which were the eigenstates, and then this relation was true, but this relation is not true when these are not energy eigenstates. So, and that could be the case often. We might be interested in knowing the transition between two states which are not energy eigenstates. So, then this relation is not true, then you have to do the hard work. Then you have to use the you have to express this in terms of the energy eigenstates and see, and there will be some complicated factors coming out. This won't be the simply equivalent, and that is often not easy to calculate. So, in the problems where the interaction picture is useful is usually when these things are energy eigenstates. So, in that case we can use the formulas which we have just discussed already, otherwise we have to do this expansion, and that is another level of complication, but we will see that can be done. Actually, it is hard, but it can be done, and we will see examples of that. Okay. So, now let us use the equation 14 and 15 and use the dictionary in the last lecture which translate between interaction Heisenberg and Dirac and Schrodinger picture, and multiply equation 14 by US naught T T naught in the front to expand and express VIT in terms of US to obtain the Schrodinger picture propagator. So, you have learned what is the UIT T0. Now, we want to write down the express it in terms of the UST T0. We know the relation between these two. So, the UST T0 will, when you do that, will simply become this series solution. So, that is a little bit of algebra which you can work it out. So, in compressed form, this is the UST T0, and we will now look at the physical interpretation of this in the part 2 of this lecture. Okay. That is where I stop this part.